Science in the AM, grade 9. I'm your host, Joel Shandelka. Anyways, you are giggling. That's cool. We're just taking a look at board diagrams in progress for this class. We're starting with the simplest. Board diagrams are a way of showing how electrons are organized with different levels. And it's useful. It's not visually what you would see if you could see an atom, but it's helpful. The first two on the periodic table, the first two elements, hydrogen atom, we're going to look at, and a helium atom. And I take a look at the periodic table, hydrogen, one proton, and neutral hydrogen, that means would have one electron, right? One positive, one negative. This is very easy then. By the way, I'll just backtrack. Hydrogen and helium have one ring around them because they are on the first left to right row. Okay? So the first row, one ring, and one electron for hydrogen. So we just place it at the top. Oh, then there it is. Place one electron. It's that simple. Helium has two. And we group two electrons together. And that completes the first row, the first ring. More diagram. You just put this, yeah, now this doesn't show a lot, but I need to show the first two. Okay? Make your dots, don't make them specks. I need to know that you've actually put it down there. So make it a round dot. Okay? So that's that. Hydrogen. Now they get more complex. By the way, we'll only do more diagrams for the first three, little bit into four, only potassium and calcium, but really they're only useful for the first three rows. Okay. Boron and oxygen. Let's try those. We'll do boron first, obviously. Now they're both in the second row, or second period is actually periodic. So we're going to use two rings. So draw B for boron, two rings, as best you can. And all we do is count from left to right on the periodic table. I'll show you what I mean. So we count hydrogen and helium. Boron has all the electrons that hydrogen and helium has in its first shell, we're going to say for Bohr, or for Bohr diagram. So we start with boron. 1, 2. We counted the two electrons on the first level. Boron is in the second level. And we have on the second level, we count from lithium, beryllium, boron, right? There's 3. Now, here's the thing. You notice that altogether there's 8 spots in the second row. I'm going to draw something that you're not going to draw just because it will disappear on purpose. But we would think of it this way. It has to fill up 8. So you think of this circle as a sort of a 4-sided box within the circle. And you would actually fill it up. If I was going all the way to neon, I'd go 1, 2, 3, 4, 5, 6, 7, 8. You don't double them up until, and they're disappearing now, it's disappearing. You don't double them up until you get all the way around. Now, boron isn't 8 electrons on that second level. It only has 3. And I just tend to think of it as, boron altogether has 5 electrons, but I think of it as 3 in that second shell. 1, 2, 3, lithium, beryllium, boron. So I go like this. Am I on regular? 1, 2, 3. So I sort of think of that as 4 sides on a circle. And I don't double anything up. Not until the 5th one. And oxygen will display that. Okay. Oxygen. We're done with boron. 5. Grand total of 5. Oxygen. So oxygen's also in the second row. It's the 8. There's 8 electrons. There's 8 protons. 8, atomic number 8. So it has all the electrons that you could possibly have for row 1, for period 1. So I'm going to put in the 2 dots side by side. Okay. Then we have how many spaces on the second? 1 lithium, beryllium, 2, 3, 4, 5, 6. There's 6 in the second level, right? We're going to put 6 electrons on oxygen. Now imagine this is the 4th side to fill in. 1, 2, 3, 4, and then double it up. 5, 6. Okay, so if you can tell right away that 6 is going to double up a couple, you can start with double 2. That's not quite a stretch. Okay, now this is important because it's the outer electrons that do the chemistry, that form bonds, interact with others. This is important because later on we're going to see that those 2 single electrons of oxygen on the outer shell are what forms bonds to make things like water. But enough of that. Let's just try something else. How about argon? Argon needs 3 rings because it's in the 3rd period. I'll let you just draw 3 rings. Argon. And we'll count this out. Argon on the periodic table is 18. But I'm not going to actually think about counting 18 electrons. I'm going to think of it row by row. The first ring represents all the electrons contained in the first level. That's how we organize this period. Okay? So 1, 2. That counts the first 2 electrons that are the same as up here, right? Then I know the second level, 1, 2, 3, 4, 5, 6, 7, 8, when I count up to me. We're going to put 8 electrons in the second ring. I'm going to single, 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 there's 4, then 5, double up, 6, double up, 7, 8. Try to make them somewhat symmetrical. Okay, and then argon's in the 3rd level. That is also 8 across. So I'm going to go same thing. 2, 3, 4, doubled up, 5, 6, 7. There's argon's Bohr diagram. I think you can see now why we don't go much beyond the 3rd level, right? The rings, it breaks down after this when you get to uranium or something like this. 92 electrons like the rings, and it doesn't work, basically. But this is the basis then of something we're going to look at when you're in grade 10, and especially grade 11. Lewis diagrams, which are simplified Bohr diagrams, just the outer ring. You'll see about this. But I'm going to ask you guys to do it. Bohr diagrams for. Now I said that every once in a while it'll only be calcium or potassium. You'll do a 4th level, but that's it. I won't go higher than calcium, ever. So aluminum, calcium, chlorine, and carbon. That's the Bohr diagrams there. I gave more rings than you need for things like carbon. Just because I grabbed the same set of rings for everything and just changed it. Okay? Changed up the element. 1 atom of each. Giving you time, I'm going to pause the video recording. Let's see. So if you're doing this by video, pause and then take it up after. Welcome back. Time to take up some answers. For aluminum, I see aluminum is in the 3rd period there. It's number 13. But I don't think of 13 electrons. I think of a full first ring, a first level. HH, that's 2. 1, up, 1, 2. It's got 8 in its second level, because I count from left to right, lithium, beryllium, all the way through neon. That's 8.
Hi there. All moderate and social courtesy. Please meet at the main door in front of the yard. Thank you.
Main door. Anyway, so if you're watching the video, go to the main door. Now, aluminum is in the third ring. That is 3 electrons. Remember, don't double up until you have all singles. Single, single, single. There we go. Yes. Easy question. Singles. These singles get lonely, though. They want to double up. Ever think single cheeseburgers get lonely? Like double cheeseburgers are happy. Anyways. Well, let's see here. Calcium. 4, and this is one of the few times I would give you something that has a 4 ring. I will not go past calcium. So it is everything in the first, second, and third. Second and third each have 8 electrons. I'm going to just kind of quickly zip through it. 2, 8, and 8. 8 for the second. Double up. The single cheeseburgers become happy double. Third row. Doubles. 500. Okay. Calcium is in the 4th row. We're going to use the 4th ring. 1, right? 2 electrons, single, single. It's the outer electrons, I'm repeating myself, but it's the outer electrons that do the chemistry. And that predicts what kind of bonds it will form, what kind of compound. So this is important. On the lower line, chlorine, 3rd row, 17. So that everything you need from the first grid. 1, 2 electrons. It has a complete second shell. 1, 2, 3, 4, 5, 6, 7, 8. And in the 3rd ring, we're going to count again 1, 2 from sodium over 11, 12. 1, 2, 3, 4, 5, 6, 7. So we need 7 on the other ring. 4, start doubling up. 5, 6, 7. It has 1 single. That means when it forms compounds, it actually wants to do one thing with this single. Singles are lonely. It's sad. Single cheeseburgers are just sad. They want to meet. Same with single electrons. Carbon. Yes, there's more rings just because they kept using the same ring. Carbon is on the 2nd ring. Doesn't use the 3rd ring even though. But everything in the 1st ring. Happy 1st ring. Then carbon. 1, 2, 3, 4 over. That's 4 electrons in the 2nd. That's 4 singles. That's really important in biology, because there's 4 singles. That means there's 4 opportunities to double up, to bond, and it forms a lot of compounds. And it's not a mistake that life, the major atom that's the building block of life, is carbon-based compounds, because it has so many different varieties of compounds to form because of the 4 spots available to make covalent bonds, molecules, biological molecules. Okay. We're going to look at something, though. And just briefly, we'll just see something, and I'm going to get you to watch this. Okay? You don't have to copy this down. Hydrogen and oxygen we're well aware of, and the compound that I keep using is H2O. Now, said singles get sad and lonely and they want to double things up. Hydrogen, to complete its shell, would need, because it's on the first ring, only needs one more electron, and then it's got a complete shell, right? So somehow hydrogen wants to share with something else, and it wants a second electron. Oxygen wants, it has two symbols. It wants one right there, and it wants one right there, right? That's what that predicts. So, what's the formula for water again? H2. Oh, okay. That means we need, oh, I'm trying to grab this, 2 hydrogens for 1 oxygen. Then what? Well, does it make sense? I'm going to just grab this. We're going to ignore this hydrogen that originally was there. We're going to say, well, what if hydrogen shared that electron? What if this hydrogen shared there we go, that electron there? We're ignoring, I'm just going to say we're only looking at these here, okay? We're ignoring that other. You guys see how this predicts the formula? And we actually simplify this in grade 10. Depends who teaches grade 10. Grade 11, 12, and stuff like this. When you look at diagrams of molecules, you'll actually ignore the inner ring electrons. And it's something called the Lewis diagram. And you'll only look at the outer ring one. And it simplifies how you draw these structures. And you do that somewhere. So I'm just showing you why these are useful. Yeah. Let's take a look at this together. Sodium chloride, before and after. Before. We're going to draw this. And it does need to. We're going to fill in the dots. I'll let you get caught up here and we'll do this together. Think of a sodium atom and a chlorine atom. So, 2 different colors only just to organize thoughts. Red, sorry, no particular reason why red. So sodium is in the 3rd period. That's number 11. So it has everything on the inside. Ring, first ring, first shell, first level. 8 on the 7th. And one lonely little guy on the 3rd, which is 1 at the top. Chlorine, 17, that has 5 in its 3rd shell, or 5, 7. 5, 7, that. Okay. So 2 on the 1st, 8 on the 2nd. Oh, I said it didn't use a different color, sorry. You don't need to use a different color, it's just really make something pop up. There we are. That's what we should have before. Okay? Those are just the plain atoms not charged. The electrons are the same as the number of protons. This is how we're organizing them. What kind of compound. Well, I can see this guy has a single. This guy has 1 single. I think they can help each other out. But unlike the water example, which is a molecule, where they form a covalent bond, I'm getting into exactly why, they share their electrons. These are ionic. And we remember when we read through, it tends to form a metal and a non-metal. And sodium is a metal, definitely a metal. It exploded with water, right? And some. And it actually loses an electron. So this drawing, your drawings are static, so you can't do this. But this drawing, this electron is lost and transferred over to here. This is what I used to do. Now, what is the consequences of that? We're going to draw this before we have it. And what I just explained was sodium wants to lose one electron, then it'll have a full shell and all paired up electrons, like neon. The closest, not the closest, noble gas. You know, when I use handwriting to writing. And chlorine wants to gain that one electron to have a full shell, like argon, its closest noble gas. And I'll tell you about that after. Because the noble gases are the 18th column family. And they have full electron sets. They're completely happy. Everything's doubled up. And I'm saying chlorine wants to gain, sodium wants to lose, as if they're thinking. They don't think. I'll tell you about this after. If we hit the bell, we hit the bell, we'll finish this. I'll talk to you guys about charges in a second. Just making sure everybody's got that sentence written down. Okay. Now here's the thing about charges. Before, when I have this set up, sodium has 11 protons, positive, 11 electrons, so it's a zero charge. If I take away one negative, that means there's 10 electrons, 11 positives, protons. What would the difference? Is it positive or negative? Really? 11 positives, 10 negatives. The difference is positive 1, right? So it's going to, when I remove that electron, have a positive 1 charge. Chlorine, on the other hand, before, green, has matching numbers of protons and electrons, right? So it's 0. But then I add one extra electron, because 18 electrons. There's one extra negative. If you go 18 negatives, 17 positives, that's a negative 1 charge. So what we're going to do on the after that, see this, right, is what we just talked about. Positive, you see how the sodium has a little positive, has like an exponent. But see how this bond doesn't make it look as high as an exponent should. See how with a minus up high, kind of in the spot where an exponent is. I'll draw this up. Sodium, 1 less, 10 electrons. So it's going to have all of those inner electrons. And I'm just going to double up straight. They're no different. That's my 10. The 11th one, I just sit it here and I'll put it in later. Chlorine, on the other hand, started with 17 electrons, and I'll make the diagram that we had before. Now, you don't have to make your electron a different color if you just got one valence. But there, your red dot That's that added in electron. That's why it has a negative charge. Ones that are only common. With a metal, such as sodium, sodium chloride. Get that jotted down. We're good for now. And that's kind of just a sneak peek of what you're going to see in grade 10, where this is going. Okay? Thank you, guys. You did it. 1 minute remaining in class.